These are the notes on valence electrons. Valence electrons are much easier than the electron orbitals that we did last time. So this should be relatively easy. But before that, let me do a quick review of what we've learned so far. The periodic table looks like a city skyline. The reason for that are the electron orbitals. This is what leads to periodicity, like the days of the week, properties of elements repeat. Electrons don't like each other. They find each other repulsive, literally. And people use that word incorrectly, but I am not. They push each other away. And two electrons can tolerate each other, but that is only because they have two different spins. There is no third spin. So remember that electrons often wind up in pairs because one electron has an up spin like Voltorb, the other electron has a down spin like Electrode. Energy levels. In the textbook, they refer to these as shells, like shells of an onion, shells of an egg, I don't know. I prefer calling them energy levels. Energy level 1 has one orbital. It is an s. Energy level 2 has two orbitals. It is an s and a p. Energy level 3 has three orbitals, an s, a p, and a d. Energy level 4 has all four orbitals, s, p, d, f. How do you remember those? You remember them because of Sally's poor dog, Flatulated. This is the mnemonic device only to remember the sequence of orbitals in an energy level. If you look on the periodic table, you can see where these orbitals are being filled because there is an s block on the left, there is a p block on the right, and in the middle we've got the f and the d block. Now, we talked about why those fill in that order and why we say Sally's poor dog flatulated already, but just keep in mind, you know for sure, if the element is located in one of those areas on the periodic table, then that is the last orbital that is being filled in that element, at least in the atom. The only exception is helium. Look, helium should be in the s block, but it's thrown to the right because it's much like the elements below it. So that's the only exception. The German word Aufbau means building up, building off. You got to put in energy level 1 before you start energy level 2. You got to complete energy level 2 before you start energy level 3. That is what Aufbau means. Even more than that, you have to finish the s orbital in an energy level before you go to the p orbital. Now, there are a few exceptions to this. I did not mention those. You are not expected to know those. There are a few times when this can be violated, and we have not discussed those yet. So you wind up with a sequence. If you watched my example on electron configurations, the electron configurations example, I go through this whole thing, and you get to see how these fill. So it gets a little tricky, I must admit, in the 6th and 7th period, down at the bottom of the periodic table. That's where things get tricky, and you get 7, 5, 6, 7, what? But other than that, it's fairly straightforward. It's a lot like reading a book, okay? And the d orbitals have an exceptional rule, shave before dressing. You fill the next s before you start filling the d for that energy level. We talked about the atomic size trend. This is probably the trickiest trend to understand, and yet the most important trend for understanding what elements are like. Basically, the point is, if it didn't make sense the first time, elements on the left are bigger than elements on the right. That's the important part, because elements on the right have more protons in their nucleus. They draw the electrons in closer. They make the atom shrink as long as it is in the same energy level. And then when you burst open a new energy level, well, all bets are off, it gets bigger again. So as you go down the periodic table, well, that's just obvious, they get bigger. But as you go to the right, they get smaller. And that is the counterintuitive part, and that is the reason that we have metals and nonmetals. All kinds of things depend on this trend. So now we get to the very easy part, the valence electrons. Valence electrons are not hard to understand. Once you know them, you will know them. You will get them right flawlessly as long as you are careful. And there's only one exception, and guess what it is? What was the only exception in the electron orbitals? Oh yeah, helium. Well, guess what? That is the only exception with valence electrons as well. So what is a valence electron? Well, valence means strong. So valence electrons are the powerful electrons. They are the ones that do almost everything in an atom. They are electrons found in the highest energy level of an atom. I like to call these the business electrons because they get down to business. They are involved in every chemical reaction. They are involved in every bond. In fact, only valence electrons are involved in bonding. And these are the easiest electrons for an atom to lose. These are the only electrons an atom can normally lose unless it becomes plasma. So it's very important. These electrons are the ones that can change, that can come and go. These are the ones that have reactions and bonds. Very important to chemistry. The good thing about valence electrons is that they're very easy to determine, at least for the S and the P block. They are super easy to determine. What do I mean by the business end? Well, that's the business end of a shark, and that's the business end of a scorpion. You might do okay if you run into the other end of the shark or the other end of the scorpion. I guess scorpions can still pinch with their pincers, but it's really the tail of the scorpion that can be deadly. It's really the mouth of the shark that causes the most damage to surfers in wetsuits that, by the way, look exactly like sealskin. So that's why surfers probably shouldn't wear those black wetsuits, but that's the fashion trend. So anyway, that's what I mean by valence electrons being the business end of the atom. They are like the mouth of the shark or the stinger of the scorpion. So if you're talking about hydrogen, now notice I'm representing it totally differently. Forget about what I showed you last time. Now I can use a much more simplified method, and I will. The simplified method is this. I'm going to show a nucleus, and that is represented by the charge in the nucleus. You could also call that Z, okay? Or the atomic number is also the charge. So this is +1. Well, that's got to be hydrogen, right? Hydrogen is number 1. If you have a +1 nucleus, well, then you only need 1 electron. Electrons are -1. Only 1 electron to cancel that out. I'm showing that electron going in a circle. That circle represents the first energy level, as if it goes around like a planet. Electrons do not go around the nucleus like a planet, not even close. They buzz around more like moths around a light. Moths around a light at night. That's how they buzz around the nucleus. So I'm representing that 1s1 electron in this way. Notice that the 1s1 is actually much more complex than the structure that I'm showing in my diagram. Okay, this is the planetary model of an atom. So even though these planetary models of an atom are very simplified, keep in mind that they are actually equally wrong. The other models you've seen that I showed you before, well, that doesn't really show it either. So no matter what you see, any atom that is represented in any way is going to be somehow wrong. So this is just another way of thinking about it. The reason we use this model sometimes is because it's simple, easy to understand. Okay, so now we've got 2 protons in the nucleus plus 2. What element is that? It's the second element. It is helium. Helium has a 1s2, but you know what? How important is that? All we really need to know is there's 2 electrons in the first energy level. Remember, the superscript, the little tiny 2 there, is telling us how many electrons are there. And guess what? Both of those are valence electrons, because hydrogen and helium only have valence electrons. It's only when we get to the next one, lithium, okay, that we start to see a difference, where not every electron is now a valence electron, only some of them are. Okay, so we've got the first energy level. Of course, that can only hold 2. Then we've got another circle. Guess what? That doesn't represent the 2s. That circle represents the entire second energy level. So right now we only have 1 electron on it, but that represents the entire second energy level, or as the textbook would say, the second shell. Okay. Now notice there are 3 protons in the nucleus, so it needs 3 electrons to neutralize those. 2 of them fit in the first energy level. Those are the lucky ones. That's where electrons would love to be. One of them has an upspin, one of them has a downspin. I'm not really showing that, but you can see how they're opposite each other. I guess in a way that represents that. But you can never fit a 3rd electron into the first energy level. It has to go to the second. That is Aufbau. That's what Aufbau means. So that electron in the second energy level is on the outside. That is the one that is going to come into contact with other atoms. That is the one that is going to make chemical bonds. That is the one that is going to get lost. If any electrons get lost, it's going to be that one first. Okay, unless you make plasma, that's the only one that's going to get lost. So let's forget about those other ones. What do they do, really? Let's fade those away. They're gone. But wait a second. They're there, I'm just not showing them. So what effect are they having on this atom? Well, they are not valence electrons. In fact, lithium only has 1 valence electron, and there it is. It's the electron in the second energy level, because that is the highest energy level that lithium reaches. So electrons in your highest energy level are your valence electrons. So what effect do those other 2 that I faded out, what effect do they have? The only thing those electrons do is they change the effective charge of the inner atom. The effective charge of the inner atom of lithium is not +3 because it has 3 protons in there, yes, but it also has the 2 electrons in the first energy level. So that's +3 minus 2, what is it? Oh, the effective charge, ZF, effective charge of the inner atom, is +1. Weird, because even though there are 3 protons in the nucleus, you would not know that if you were outside of the first energy level. Outside of the first energy level, in the second energy level where that electron is, it's not feeling the full +3. It's only feeling a +1, which is actually exactly what hydrogen has. Hydrogen has a +1 charge of the nucleus. And yet, remember that these charges, they don't last forever. These electrostatic charges, they drop off with distance very quickly. And this electron is farther away than the one that was in hydrogen. So this is feeling a +1, but at a greater distance. And that's not a lot of pull. That's one reason why this electron can be easily lost. Let's go to the next one. Well, this is the next one, so it's got 4 protons. What is that? Must be beryllium. Oh yeah. And beryllium, same thing. Some of them are inner electrons, some of them are valence electrons. By the way, valence electrons used to be called outer electrons. If you do some research, if you look things up, you might still see that. However, outer isn't enough. It doesn't get the point across. They're not just on the outside. They are by far the most important electrons in an atom by a ridiculous margin. Okay? So calling them valence gets the point across. They're the strong ones, the powerful ones, not just outer. So we don't really use that terminology very much anymore. Now notice, if I fade away those inner electrons, you can see that there are 2 valence electrons. 2 valence electrons in beryllium. So what is the effective charge of the inner atom? Well, here's an easy way to figure out the effective charge of the inner atom. You don't really have to do heavy-duty math. All you have to do is think about how many valence electrons are there. Put a plus in front of that number. Guess what? That is your effective charge of the inner atom. It's always equal but opposite to the charge of the valence electrons. Well, valence electrons are always negatively charged. So if you have 2 valence electrons, which have a -2 charge, well, there must be an effective charge of +2 attracting them. So they are not feeling the full pull of the nucleus. This is critical. This is very important. They're not feeling the full +4 attraction to the nucleus because it is being shielded. That's the word we use. It is being shielded by those inner electrons. It's being blocked from them. So all they are feeling is the +2. Well, guess what? That is twice as much effective charge of the inner atom than lithium experienced. So when we were talking about the atomic size trend, this is the part I could not really get to. Actually, it isn't just increasing little by little as you go across, it's increasing dramatically. It's doubled just now, going from lithium to beryllium, just going over by 1. The effective charge has doubled. That has a huge impact on shrinking the atom down. So beryllium is way smaller than lithium. It's not even close because it has twice the effective charge of the inner atom pulling on those valence electrons. And it is the valence electrons, of course, that make the size of the atom. They are on the outside, they are the perimeter, they make the atom big or small. It's them that does it. That's bad grammar. So I'm not really going to go through every single atom in this way. I just wanted you to get the point as we go across. So now I've skipped ahead. Notice what's happening here. Wait a second. I've got 1s2, 2s2, 2p6, but I only have 2 circles. So remember, the first circle is the first energy level, or shell. The second circle is the second energy level. So I'm putting all of those second energy level electrons on the same circle. So who can tell me how many valence electrons does this element have? And what element is this anyway? It is element number 6, atomic number 6. It has a +6 nucleus, that means 6 protons. It must be carbon. So carbon, of course, needs 6 electrons. But how many are valence? This should not be hard. How many are valence? Let me fade away the ones that are not valence, the inner electrons. And now we are left with 4. Notice that if I add up the superscripts, those little 2's, I can tell from the electron configuration. Those are the electrons that are in the second energy level. Or I could just count them in my diagram above. So again, what's that effective charge of the inner atom? You should be able to tell me by now. It's always positive, by the way. Effective charge of the inner atom is always positive. And what's the number? You should know this. 4. Why is it 4? Because there are 4 valence electrons. That's the easiest way to always get it right, to figure out the effective charge of the inner atom. It's the number of valence electrons with a plus in front of it. So the electrons in the lower energy level are not valence electrons. They shield the charge of the nucleus, and that's really all they do. They do very little other than that. Unless you get to plasma, where yes, they can be ionized. If you have lots and lots of energy, they can be ionized. They can be knocked away. Normally they do nothing other than shield the nucleus. So now we have this one. +8, what is that? Oxygen. Oxygen is element 8. They could have called it octogen, I suppose. And it has 8 total protons, which attracts 8 electrons. But how many of those are valence? You should be able to get this by now. How many of those are valence? 6. How do I know it's 6? Because I can add up the superscripts of all the electrons in the highest energy level that is reached, which is the second one in the case of oxygen. So those 2 inner electrons are shielding the nucleus. So what is the effective charge of the inner atom? What's the effective charge? You should be able to get this as well. +6. If you're catching on, you would have known that. So think about this. Remember that lithium had an effective charge of only +1, and then beryllium doubled it and had an effective charge of +2. By the time we got to carbon, okay, we had an effective charge of +4. That is 4 times as much as lithium had. Now we are at oxygen. That has an effective charge of +6. That is 6 times as much attraction as lithium had, effective charge of the inner atom. So that is why oxygen is much, much smaller than lithium. That is why oxygen is a non-metal, because it's a smaller atom. Then we get number 9. Number 9, what is number 9? 9 protons in the nucleus. Fluorine. Fluorine, by the way, is the most commonly misspelled element. It is spelled as if it were fluorine, okay? It is not like fluorine. It's F-L-U-O, and a lot of people get that wrong. That is the most frequently misspelled element by quite a margin. And, well, it's got 9 protons, but how many valence electrons does it have? Only 7. Because, of course, the 2 inner electrons only shield the nucleus. So what is the effective charge of the inner atom? What's that effective charge? It's almost like 1 electron is missing there, isn't it? Effective charge is +7. Now it looks like, the way I've drawn this, that there's just sort of like one thing missing. One more electron would make this complete. And that's exactly the way that fluorine behaves. Fluorine will beg, borrow, or steal to get that last electron. And that is one reason why fluorine is such a dangerous element to have around in its pure form. Not as dangerous when it's in a compound, like fluoride compounds in toothpaste, not so dangerous. But if you have pure fluorine in the room, I would run. We'll talk about that more later. So fluorine is 9 out of 10. Almost there. What would be better than that? Oh, I know. 10 out of 10. Now we come to perfect 10. +10 nucleus. What element is that? That is neon. Perfect, perfect little neon. Now neon doesn't have 10 valence electrons. Who can tell me how many valence electrons neon has? It has 8. And 8 is the magic number in chemistry. 8 gives rise to the rule of octaves, or the octet rule, where having 8 electrons is just the best you can do. If you have 8 valence electrons, I should say, if you have 8 valence electrons, then you're all set. That means you don't have to worry about anything. You've got what you need. You don't need any more, and nothing else can get in there. You're sort of protected from the outside. Plus, it makes it a very small atom. Why does it make it a very small atom? Well, who can tell me what the effective charge of the inner atom has to be? If you have 8 valence electrons, it has to be +8. That is the highest effective charge that you can have of the inner atom. So remember, this is 8 times the attraction of what lithium had. So no wonder these noble gases, like neon is a noble gas, are so tiny. They have so much pull on that second energy level, they pull it in as close as possible. This is one reason why noble gases are so incredibly stable. They're very tiny. Being tiny makes you more stable. Also, nothing is sort of sticking out to engage with surrounding elements, which is why they almost never react. So having 8 valence electrons, that is the way to go. That's the ticket. That's what every element would love to have, but very few elements actually have that. In fact, only the noble gases have 8 valence electrons, and that makes them the most stable of all the elements. The only noble gas that doesn't have 8 is helium, because it only needs 2, because it's in the first energy level. And of course, helium in many ways is often the exception to all of our rules of chemistry. Now what about this one? Well, now we've just gone a little bit higher. We've got look at the nucleus. We've got +11. What's number 11 again? Na. What does Na stand for? Oh yeah, natrium. But natrium is the old name for it. We call it sodium. Sodium. And by the way, there's a lot of sodium in your body and in the ocean all over the place. It's a very common element. So let's see, sodium has 11. So we just saw that neon had 8 valence electrons. I wonder how many valence electrons sodium has. Who can tell me? How many valence electrons does sodium have? Wait a second. Did he put in a new circle? Mr. Pemble just put in another circle. Why? Because notice, now we are in the 3rd energy level. So each energy level gets a circle, right? So now, how many valence electrons does sodium have? Well, let's blur out the ones that are not valence and see what's left. Oh yeah, really, there's only 1 left, isn't there? That's because that's because there's only 1 electron in the highest energy level, which is now the 3rd energy level. So what is the effective charge of the inner atom? You can still do it the same way, by the way. You should be able to get this. +1. So why is it +1? Because all of those other electrons, all 10 of them, are inner electrons. They are shielding 10 of the 11 charges from the nucleus. So if you're out there in the 3rd energy level, it's kind of lonely. You're pretty far away from the nucleus now. You're 3 rings out, and all you're feeling is a +1 charge, which isn't that much. That's what hydrogen has, but you're farther away, which makes it weaker. So in the case of sodium, going from 10 to 11 causes all the difference in the world. Having that 1 extra electron in the 3rd energy level makes sodium incredibly reactive. You're going to see that in the videos of the demo. I would have liked to have done the demo for you in person, but since we're in these circumstances, you'll have to watch the video. But you can see that sodium is nothing like neon. It's not a very stable, unreactive element. In fact, quite the opposite, is one of the most reactive elements. And it's all because that 1 little dangling electron way out on the edge, it's kind of up for grabs. Anybody could come along and take that. The slightest bit of energy could knock that away or take that away or make a bond with that very easily. And that is the problem with sodium. So now we come to the next one, +12 nucleus, the next one over. If you look at the periodic table inside the back cover of your book, it is magnesium, named after Magnesia, Greece, which you probably never heard of. Magnesium has just 1 more proton, which attracts just 1 more electron. Well, that can go in the 3rd energy level. The 3rd energy level was just getting started with sodium. There's plenty of more room in the 3rd energy level. But wait a second. That is now how many valence electrons? How many valence electrons is that? Let me blur out the other ones. 2. There are only 2 valence electrons in magnesium. So what is the effective charge of the inner atom? Oh yeah, it must be +2. So that doesn't sound like much, right? But that is double what sodium had. So even though magnesium is right next to sodium, it is nowhere near as reactive. It's nowhere near as big as sodium because it has twice the effective charge of the inner atom, pulling those valence electrons much closer in. It makes a huge difference. And this pattern repeats again and again and again. And what you find is that increasing the effective charge of the inner atom is the main explanation for the reason that atomic size reduces as you go across 1 period or 1 energy level. That is the #1 reason. So last time I sort of glossed that over. I didn't go into detail, but it actually happens much more rapidly than what you would normally expect when you consider the effective charge of the inner atom. Going just from 11 to 12 doesn't sound like a big difference. But going from 1 to 2, that is doubling. That's a huge difference. Get it? So think about this. If sodium were to lose its 1 valence electron, wait a second, then everything else underneath, that's exactly like neon. And neon, like I said, is perfect 10. It's a perfect atom. So why doesn't sodium just get rid of that pesky valence electron? Then it has orbitals like neon. Well, guess what? That's exactly what sodium does. Sodium will very easily lose its valence electron. Magnesium will very easily lose its 2 valence electrons so that they can be like that perfection underneath. And you're going to find that this repeats as you go on. Every element, except for hydrogen, has a noble gas configuration lurking underneath its valence shell. So sometimes it's more efficient to just get rid of 1 or 2, maybe 3 electrons, get down to what's underneath. Other times you might want to gain them. I guess I'm getting ahead of myself in terms of ions. Sorry. This brings us to the Lewis dots. I like to call them the Lewis dots, named after G.N. Lewis, the man who created them. Very smart guy, very clever chemist. He came up with this technique, which is incredibly useful, so useful to chemistry. And now the textbook is trying to just call them electron dots, as if that guy didn't even exist. I'm not going to go along with that one. I'll modify things a bit to agree with the textbook, but I'm sorry. He deserves his credit for coming up with this system. Okay? So Lewis dots are valence electrons. They are the same thing, but it's the way that we draw them. And the reason we draw them this way is because it predicts the number of bonds and sometimes the directions of the bonds and sometimes the shapes of the molecules. You can do all kinds of things using these, and we will. So these are kind of easy, but important. So don't think, oh, this is so easy, I don't have to spend much time on it. Think about it this way. This is so easy that I can get it perfect. I can perfectly understand this. Even if other concepts in chemistry might be a little harder to fully grasp, this one is not. And so as long as I get this perfect, I'll get all those questions right, and it will really help me in chemistry. And it is very important. So I don't want to downplay the importance just by saying that it's easy. Now look at this diagram that I've made, and notice that all of the elements on the left side in the very first column, going from H down to CS, from hydrogen down to cesium, they all have one little red dot next to them. Okay? That is their valence electron. So Lewis dots do not show all the electrons, they only show the valence electrons. And here's the great thing, Lewis dots do not really apply to the D block, and they definitely do not apply to the F block, so we can just sort of cut those out of the periodic table and squish the periodic table like I've done here, squish it together like I've done here. So it saves a lot of work because there's a lot of elements that are in the F and the D block in the middle of the periodic table, but we don't worry about those with Lewis dots. And do you know what? It's okay because those elements, honestly, they don't come up as much in a lot of situations. You'd be surprised. These are most of the important elements. The ones you have here are the ones that we see most frequently. Okay? There are some we have to deal with in the D block. I'm not saying they're not important, but these are definitely the most important ones right here. Okay? So notice that after beryllium, it goes straight to boron. Where's that big space that occurs there? It's missing. Okay, so I've squeezed them together. Notice in the second column, as you go from beryllium down to barium, well, they all have a dot on each side. They have 2 Lewis dots. And then in the boron column, the one that has a B on the top, it's actually called the aluminum family. We'll talk about that later. Boron got disowned by its family. There are 3 dots on 3 different sides. The carbon family, the next one over with a C on the top, has 1 dot on all 4 sides. Think of it as being 4-sided, like a square, and that the dots can go on the different sides. Everything below the carbon, notice, but look at silicon below it, Si, look at Ge, germanium, look at Sn, tin, and Pb, lead. All of those have 4. Interesting. And then look at the nitrogen family with N at the top. Well, they all have, let's see, there's 2 on the top, 1, 3, 4, 5. Oh, wait, there's a pattern here. The next one is the oxygen family, which has 6. The next one is the fluorine family, the halogens. It's not the fluorine family, that has 7. And then there's the noble gases, which have 8, except, of course, for helium. Okay. So there's a pattern here, and it's a really easy pattern. Everything in the first column has 1. Everything in the second column has 2. Third column has 3. Fourth column has 4. Fifth column has 5, sixth column has 6, seventh column has 7, eighth column has 8, except for helium, which only has 2. Now, if you notice, helium has 2 electrons, those dots, put together. And if you look over back at the beryllium column, which is called the alkaline earth metals, okay, they only have 2, but they're spread out on different sides. So that is important. That is the way that we show Lewis dots. So let me show you the technique for drawing Lewis dots. Lewis dots show the valence electrons around the element's symbol. So think of the symbol like I'm showing it here with just an X. That's not like any particular element, just generic X. The symbol of the element represents the inner atom, okay? And then the dots we put, let's say maybe it has 1, we put it on one side. It does not matter at all which of the 4 sides I put that dot on. Okay, it just has to be clearly shown on one of the 4 sides. Think of the X as being inside of a square, okay? You just don't want to put it like at the corner of the square. That would be weird, okay? If it has 2 valence electrons, well, then you put them on 2 different sides. The only exception to that is helium, as we saw, where they are put together. Okay. If you have 3 valence electrons, well, then you've got 1 on each of 3 sides. And if you have 4, then they're shown on 4 different sides. So the only important thing here is that they're shown separately, individually, on 4 different sides. Then, after you have 4, they begin to get paired up. When you have 5, you begin to have a pair, like this. It is important that one of the pairs is shown and that the others are shown individually. Okay. When you have 6, well, now we have 2 pairs and 2 that are individual, left alone, individual electrons. If we have 7, we have 3 pairs and 1 that's left on its own. And finally, when we have all 8 of the octet, we have 4 pairs of electrons. So it turns out this tells us a lot about the way that atoms behave. It tells us how many bonds they can make, what kind of ions they will make. All kinds of things come out of this. And it's really easy. So because of the big gap in the middle of the periodic table, what you might want to do is count 1, 2 on the left, and then on the right side, instead of counting up, you might want to count down from 8, because the noble gases are 8, and then the halogens, the family right next to them, is 7, and then you could keep counting down, 7, 6, 5, 4, 3. That's probably the easiest way to do it, and then you always have to remember that helium is that exception. So this is how we show Lewis dots. This is going to be critical for a lot of things we do in chemistry. So even though it's easy, make sure to get it right. Try to get it 100% correct. So here's an example. One of these is wrong. I wonder which one. Let's see. Argon, well, that's a noble gas. It should have 8. That looks good. Hydrogen, yeah, hydrogen has 1 valence electron. Oh yeah, magnesium, I remember that was doubling sodium, so it had 2 valence electrons. Carbon had 4. By the way, the fact that carbon has 4, that is correct, is one of the most important reasons that carbon is the building block of life, that we'll get back to later. Aluminum has 3. Yeah, aluminum does have 3. Oh yeah, I see the mistake. What's the mistake? Fluorine is a halogen. Halogens are right next to the noble gases. So how many valence electrons should fluorine have? Should the F have? It shows 6. That's not right. It should be 7. There we go. So that is now all correct, and you should be able to recognize that. After a little bit of practice, you should be able to get good at these, and then we're going to need these like crazy when we go into chemical bonds. So please make sure that you fully understand Lewis dots before we move on into our next unit. But really, showing valence electrons with Lewis dots is really all there is to it. Figuring them out is pretty easy. Effective charge is pretty easy. It's the number of valence electrons with a plus in front of it. So all the things from today's notes should have struck you as way easier than the electron configurations that we did last time. So now you can finish your electron orbitals worksheet. Now you should easily be able to tell how many valence electrons there are. Put that number in the column on the right, and you should be able to draw the Lewis dots. Please don't forget to draw the Lewis dots around the symbols of the elements on the left-hand column on the electron orbitals worksheet. So it is due today. You should be able to finish it in just a few minutes as long as you did all the other work the other day, and submit it to me. Okay? And we will go on from here to learn more about atoms and the way they behave. That is the end of the notes on valence electrons, which is the easy stuff in this unit. That's the easiest thing we're going to probably learn for quite some time.